Hi, everybody. So let me introduce the SIR model of epidemics motivated by this coronavirus outbreak. And we're going to try to model the progression of this epidemic, in this case in Italy, but we'll substitute other places as well later on. Okay, so this is the model here. Um, and it's there's three variables. There's the S stands for susceptible, I for infected, and R for recovered. Now, recovered uh, is either the ones that gained immunity or people who died. So essentially, sometimes it's also called stands for removed from the population. Okay, and so let's run through this model. So the rate of change of the susceptible initially, when the virus is first introduced into the population, everybody is susceptible in the population, and maybe you have like one infected, let's say, and 60 million susceptible in case of Italy. Okay, and nobody is recovered yet. So the way the infection progresses is that the infection happens when a susceptible individual comes in contact with an infected individual, okay? And the number of contacts is proportional to the product S times I, right? The more infected individual you have, the more there's going to be contacts, and same with the more susceptible, the more contacts, okay? And each time there is a contact that happens between two individuals, there's some probability of infection. So this constant here stands for the probability. This n, by the way, is a normalization constant, is the total population. Okay, so it's just a way to normalize the system. Okay, so minus sign represents the fact that now susceptible, once the susceptible is come in contact with the infected, they with some probability become infected, they are no longer susceptible. So that's hence the minus sign. And then they move into the infected class. Okay, so this term here is the same as that term, except with a plus sign. So they go from being susceptible to becoming infected. Okay. On the other hand, the infected individuals uh, eventually become removed from the system either by recovering from the disease or by dying. Okay. And it happens at some rate that is proportional to the number of infected individuals. And again, the same story. They go into the recovered class. So this term is exactly the same as this one with the difference of the sign. So that's the model, very simple model. And our goal here is to estimate the parameters of this model. And in particular, there's basically the two critical parameters, beta and gamma, right? Beta is the rate with which how virulent in fact the virus is, essentially, how easily it is transmittable, and gamma corresponds to how fast the population recovers from the disease. Okay. So let's estimate those two parameters. And so what we're going to do is the following. Let's look at the onset of the infection. When the infection just starts, as you can see, today is March 31st. At the onset of the infection, we see an exponential growth everywhere of the coronavirus. And the reason for that is because if you look at the equation for the infected, essentially at the starting point, S is roughly proportional to n. In other words, everybody is susceptible. And so this equation becomes di dt looks like I times beta minus gamma, right? And this is the exponential growth. The solution is, of course, is e to the beta minus gamma times t, okay? So if we look at how, at the onset, how it grows exponentially, we can compute this coefficient, beta minus gamma, essentially by plotting the data on on a log graph, right? If I take the log of the infection and I plot the log of I, right? That's going to be mt plus log of I0, right? And so that's going to be a straight line, and the slope of this line, m, is going to give me beta minus gamma. Okay. So I'll show you the data later, but essentially, just by looking, let's look at the Italy data for coronavirus. When the infection really kicked into high gear initially was around end of February, and if we look at that period at the end of February, we get this growth rate. The slope m is about 0.28. Okay. Now, once the outbreak happened around beginning of March, the government imposed quarantine on the entire country, and that reduced the infection rate significantly. There was some delay with the infection rate because when the testing is performed, usually it only shows up. Well, there's first of all the problem with testing. Not everybody gets tested, but also you only get a positive test result sometime after the actual infection. So perhaps something like 1 or 2 weeks delay before the quarantine measures can be observed, due to the fact that there's not enough testing, and also due to the fact that the testing itself only becomes valid after, let's say, a week or so. At any rate, towards the end of March, where we are now, this growth has been significantly reduced to something like at least fourfold. Okay. So the severe control measures are actually working, even though every day you see still you see the numbers in Italy going up. They're not going up nearly as rapidly as at the end of February. Okay. So now the second parameter that we need to estimate, we need basically 2 parameters to estimate. Here we've estimated the difference, beta minus gamma, and let's see how we can estimate gamma directly. Okay. So gamma is the recovery rate. So if you look at the last equation here, okay, dr by t equal to gamma times I. Imagine I is a constant, okay? If I was a constant, then this equation the solution would just be this. So let's say you have some infected individuals, no more infection taking place, and then how do they recover? If initially nobody's recovered, then so r at 0 is equal to 0, then you integrate this equation, you get r is equal to gamma t I0. Okay? And the question is, when does everybody get recovered? When r is equal to I. So if I set r is equal to I here, right, then I can solve for gamma. So at time capital T, when r is equal to I, you get gamma times capital T equal to 1. So essentially gamma is approximately 1 over T, where T is the recovery period. Now from the data from China in particular, there are various estimates as to how long on average it takes a person to recover. And it seems that it can be from 2 to 5 weeks. So roughly, the range for gamma is something is in this range, from 1 over 35 to 1 over 14. Okay. So instead, then that's a pretty big range. So one other possibility to estimate gamma is to do it directly from the data. If we take the equation dr by dt equal to gamma I, and we approximate the derivative by r of t plus 1, or in general t plus some a divided by r of t divided by a, where a is the number of days, then we and so I set if you take the number of days equal to 1, then I get this rough estimate for gamma. Now, of course, in theory, this should be nearly constant, but the data is, but in real world, it varies for many different reasons. First of all, the number of tests performed, various quarantine measures, all of this changes the value of gamma. Okay. And indeed, but if we do it for the Italy data, where there's data that we have data, quite a bit of data from Italy about how many individuals have recovered, how many individuals died. Okay, and just using that data, we get these values of gamma. Depending on which period we use, if we use at the beginning of a period, at the beginning of infection, the gamma seems to be 0.038, and a little bit later it's 0.031. So slightly lower, taking longer to recover, but nonetheless relatively consistent. Okay, so now that we have the gamma and we have the m, which is the difference between beta and gamma, we can read off both beta and gamma. Okay, so using the most recent data, these are the values of gamma and beta that we get from the Italy data. Okay, and now that we have that, we can plug it in and run the program. So here, let me just walk you through this code that estimates gamma and beta. So to start with, this is the Italy data starting from February 24 until March 29th. The total number of infected, you can see on February 24 there was 229 individuals infected, and you already had 7 deaths and 1 recovered individual. And as you go on, the numbers get pretty big very rapidly. Okay, so there's this exponential growth. So in this graph here, the same numbers are shown, but on a log scale here. So on February 24th, this is the infected, or the total infected individuals. There was about 200. Okay, and by the time we get to the end of March, there's 100,000 infected individuals. And notice that this, on a log scale, it's more or less a straight line, but the slope changes. It flattens, towards the end of March. So we will use just the data at the end of March to estimate the slope here. And we use simply, here I just used least squares. So just a standard method to fit a line through, a best fit line through a bunch of data. And you can see, I mean, it looks uh, like a reasonable fit here. So this is this code here to find the M. Okay, of course, the caveat that I mentioned previously apply, namely that um, the number of reported infections is not the true number. The true number is assumed to be larger due to um, not everybody being tested, as well as the delay and the onset of symptoms, etc. But nonetheless, that's the number we'll use. Now, to estimate the gamma, here we plot at r of t plus 1 minus r of t divided by I of t as a function of t for the data through the end of March. And we get this kind of graph. Oops. We get this kind of graph. Um, and then we essentially plot like, we just take the average of these points, right? And the average ends up being around here point 0.228 in this case. Okay. So now that we've done that, we find gamma and beta, we can now simulate we can just run the simulation, and this is what we get. So here's some Python code to run the simulation. I'll put all this code online, so you can try it on your own if you like, and play around with different parameters. But essentially, this is what we get. So there's this 6 corresponds to 60 million people. Initially, everybody is susceptible, this red curve. And then we plug in these parameters that we just found, and then we start with low infection rates. Here, I'm starting with initial conditions being I of 0 is equal to 100,000, which is roughly basically the infection rate at the end of March. This is at the end of March. Of course, compared to 60 million is just a tiny fraction of that. Okay, and then using these parameters, we run the simulation forward. And this is what happens. The red curve is the number of susceptible, and the number of infected is the green curve. And it grows exponentially at the beginning, and towards, like at around 140 days from March, so that's roughly end of July, that's when the infection peaks. So at the peak, that's where you have the maximum number of, that's where you need the most medical capacity in the country. And then after that date, the infection subsides and goes down to 0 eventually. Okay. So interestingly enough, at the end of this whole infection, we observe that there is this blue line corresponds to the recovered population. So at the end, everybody is recovered. That is, either most people are recovered, and then about, depending on the data, 1 to 3% of people die. But in any case, as you can see, almost all of the population gets infected with the disease. So with these parameters that we estimate at the end of March, we get roughly, at the end of the infection, we have roughly 94% of the population was infected with the disease. Um, but there is the 6% that never got infected that are still susceptible. So the rest of the population will be infected and gain immunity to it, but there is 6% that don't get affected. Okay, and this number, what we want to do, the goal of social distancing, etc., is is multiple. But one of the goals is we don't want to have this huge number of infected where at the height of the epidemic 30% of the population is in a hospital or is at least infected. Okay, so we want to bring that number way down and hopefully also bring the total number of infected way down. So we want to bring this red curve up and this blue curve down. Okay, and so that can be done by changing parameters of the model, gamma and beta. Namely, you want to decrease gamma and increase beta as much as possible. And that will be the topic of the next video.